Now, Z-transform is a very powerful tool, mathematical tool for discrete digital signal processing. It's for discrete time signal systems. Z-transform is a companion part of the Laplace transform from the analog world. In analog world, we have the Laplace transform. In the digital signal processing, we have the Z-transform. If you still remember, why do we need to use Laplace transform in the analog domain? Is we are trying to solve for a system. It's coming from solving for a differential equation. The same thing here is people start to think about Z-transform is trying to solving for the system in the form of difference equation. The difference equation is a equation that is a convolution. Basically, it's y equal to x convolved with h. So if I have the input x, I can define my system called hn, impulse response. Then I can find my output yn. Reversely, if I have observed the input x, observed the output y, I want to identify the system to find h. Now, what I really need to do is a so-called the deconvolution to find h out of y and x. And deconvolution is quite difficult to do mathematically, or just difficult to compute. So people think about, are there any other ways that we can easily to find this, to identify the system h? Now that comes a very handy tool, which is the Z-transform. In the analog world, we have the Laplace transform. So what we have here is my system is yn is xn convolved with hn. Okay. If I want to identify the system, is I want to find the system which is in terms of its impulse response. In time domain, it's difficult to do. Now, all the things we have done is using the difference equation is we find out yn. It's just find out yn. It's in a particular format. And we can find hn as a homogeneous solution of the system. Using that, we can find the impulse response. But in general, if you got any particular input, hn, if you observe any particular output according to this input, right? The system is called the hn. Okay. We may not have the completely description of a difference equation. I may not find A's and the B's. All I have is input and output observations. Then what I need to do a deconvolution. It's quite difficult to do. So in the transformation domain, we really like to see, and we will see next time, is that this yn can transform into also a function. It's a function y, but of another variable. We call that z. And xn, similarly, doing the same transformation, it becomes a function of x, but of a different variable. Instead of time variable, I have a variable called z. Z is a complex variable. And similarly, I have this impulse response. It's hn. It's also a function of n. We can write this into capital H of z. According to the property of Z-transform, the convolution, very nice, the convolution, putting here Z-transform, becomes a product. Let me just write a product here. Therefore, the entire thing here now becomes a very nice format, which is yz equals to xz times hz. That is beautiful, because what I can do is, if I want to identify the system, hz is simply a division, because you said that's a product, so it's now becomes simply a division, y over x. Once I using that, find out my system hz, identify the system, then I can always do a so-called inverse transform, doing an inverse Z transform, and to find the time domain Hn, which is impulse response, and that describes the system. So this is the starting point why people want to use a transformation domain tool using the Z transform and looking everything at the transformation domain. So we will see that next time.